There you go. Okay, everyone, welcome to the second part of Matthijs's tutorial. Yesterday's recording wasn't complete, so I'll introduce you again for the sake of anyone who's watching in posterity. I met Matthijs in Cambridge when he was just finishing his physics PhD, physics bachelor, and starting a topos theoretic work with Peter Johnston, and then he moved on to more applied areas, game semantics, effects, dependent types, and now probabilistic programming. And he's one of the main pushers for getting Stan to be implemented in OCaml, so we can get a lot more PL technology into this. So on to you, Matthijs.
Thanks, Ohad. Okay, so in case you weren't here for yesterday's tutorial, or just to refresh your minds a bit, I'll just give a very brief summary of what we talked about yesterday. So this tutorial is about automatic differentiation, which is a technique that's really important in the back end of probabilistic programming languages to run efficient inference a lot of the time. We saw that it's very important for, running optimization on continuous parameters, but also for running various Bayesian inference algorithms. And in this talk, or in this tutorial, what I'll be focusing on is a particular perspective on automatic differentiation. And it's a programming language perspective where I want to emphasize the sort of nice functorial properties that automatic differentiation has if you formulate it on a purely functional language. In particular, I'd like to argue that you can get the definition of most automatic differentiation algorithms just by noting that they should be homomorphic functors. So they should be structure preserving functors on the syntax of a programming language. And yesterday we looked at some example automatic differentiation algorithms, namely a very simple forward AD algorithm. That was a method program on a simple first order functional language. And what it did on an example program was, let's see. Right, it sort of first, it calculated the derivative of the function the original program implemented by first running essentially the code of the original program forwards. We call this the primal calculation to just calculate the function values, but in the process storing all the intermediate values. And after that, we run another pass through the program following exactly the same control flow structure, where we replace each primitive operation with its derivative, and we compose all these steps using the chain rule for derivatives. And we call that the tangent pass. So this forward AD algorithm generates a primal pass followed by a tangent pass. So it goes through the control flow of the original program twice, basically to calculate a column of the matrix of partial derivatives of a function. Okay, then we also had reverse AD, which in many ways is the more interesting algorithm because it calculates not a column, but a row of the matrix of derivatives. And we did that by, again, running a program forwards, doing this primal phase to calculate function values, but then running through the control flow of the original program in reverse, replacing each primitive operation with the transposed derivative of that operation, and again, combining them using a sort of chain rule. And we saw in particular that duplication and discarding comonoid structure in the primal program space, or in the original program, gets translated into a sort of addition zero commutative monoid structure in this cotangent pass in reverse. So we see that commutative monoid structures are really important for reverse AD. Okay, so I'd like to start today by very briefly looking at two more automatic differentiation algorithms. Luckily, they're very simple. And then I'll move on to examining precisely the way in which these algorithms are functors and the way that they're homomorphic functors. So this is a different forward AD algorithm that I want to look at now. It's called dual number style forward AD. It's been studied in a bunch of papers recently by programming language people, but it's been known for a long time in the automatic differentiation community. And it's much simpler than the previous forward AD algorithm. Again, it's calculating a column of the matrix of derivatives. But you'll notice that the types of this program are slightly different, of this algorithm are slightly different. So it takes a a code for a function from a vector space A to a vector space B, and it produces code for a function that takes as input a value x of type A, a value v of type A, where we think of the v as a tangent vector and the x as a primal value of type A, and it returns the pair of an output, the output value of the original function and the derivative of the function applies to the input tangent vector. Right, so this types are a bit different, but it calculates the same thing as the other forward AD algorithm. But it's much simpler. You'll notice that if we formulate it this way, differentiating f composed with g is the same thing as differentiating f composed with differentiating g. And the derivative of a sine function, for example, is a function that takes an x and an x prime. So x is an input value, x prime is a tangent vector as input. In this case, a one-dimensional tangent vector, because the input is one-dimensional. And we return a pair of the function value sine of x and the derivative propagated, the tangent vector propagated along the derivative. So x prime multiplied with cosine of x. Okay. And if you look at how this algorithm then extends to programs that are built with let bindings and tuples, and that sort of thing, you'll notice something very funny. Namely, this algorithm really just preserves the structure of your original program. You'll notice that the derivative of a tuple is just a tuple of the derivatives, right? A derivative of a let binding is just a let binding of the derivatives. A derivative of a projection is just a projection of the derivatives. So this is a really, really simple algorithm. It fully preserves the structure of the original program, similar to the algorithm that Michele Pagani talked about yesterday. So what it does then is, instead of first running a primal pass and then a tangent pass, it interleaves those two passes. So on our example program, we see that the program gets sent to a program that has exactly the same control structure, but where each, I guess, bit of data is sort of doubled up, right? Y gets sent to y comma y prime. X gets sent to x comma x prime. It's the input. And at each step in the program, we're not just propagating the function value, but we're also propagating the tangent vector using the derivative, right? So this is precisely the same as the previous algorithm, except for interleaving the primal and the tangent pass. And the effect is that the types of this algorithm are much simpler and it's much easier to implement. It's also, it tends to be a bit more efficient in practice because yeah, we don't need to keep all these intermediate values in memory for so long. Okay, so now you might wonder, well, if this is so much simpler, can't we do something as simple as this for reverse AD as well? And yeah, people have tried this, many people have tried, but it's not as easy as it is for forward AD. So in some ways, the algorithm that Michele Pagani described yesterday in his talk was the best equivalent of a dual numbers version of reverse AD. So what it was an algorithm that took code for a function from A to B and produced code for a function that takes as input an A, so function input, as well as a linear function from cotangent vectors to A to some type C, and it produced an output for the function of type B together with a linear function from cotangent vectors to B, which happens to be the same as B because B is just a vector space, to C. And how you should think about this algorithm is it's calculating the action of precomposing with the transpose derivative. Okay, so again, the structure of this algorithm is super simple. The derivative of f composed with g is the derivative of f composed with the derivative of g. And this is what Michele stressed yesterday, right? This version of reverse AD is incredibly simple. But there is a bit of a problem that also came up yesterday in the talk, and that is that you need this linear factoring rule to make it efficient, right? You need some custom semantics for linear functions where we somehow push addition into the application of linear functions. And that means that the code that this algorithm generates doesn't have to write complexity if we use a standard compiler infrastructure, unless we make use of a custom interpreter or something like that, that implements this operational semantics with a linear factoring rule. And that is why I'm, in my work, I've been focusing on this other version of reverse AD without dual numbers. But it is to be determined whether this dual number version of reverse AD can be made efficient as well. And yeah, so there are two competing approaches, but this bit of code here shows how we end up duplicating the work for part of our program if we don't have this custom operational semantics, if we use this dual number version of reverse AD. Okay, so these are the 4 AD algorithms that we'll look at in this tutorial. So we have standard forward AD, standard reverse AD, dual number forward AD, and dual number reverse AD. So now you might wonder, are these algorithms correct? And like, how would you go about proving the correctness of this sort of meta program? Well, the first thing you could do to convince yourself that these algorithms are correct is that we can test them against each other, right? Because we have all these different algorithms that also are supposed to calculate the same thing, namely a derivative of a function, right? We had this finite differencing approach, which was super simple, but not very numerically stable, not very efficient. Then we had 2 versions of forward AD, 2 versions of reverse AD. We can all test them against each other as long as we take floating point precision into account. And this is really useful in practice, it turns out. But in some ways, it's not fully satisfying, right? We don't just want to see that the algorithm is correct. We want to understand why it is correct, right? We want to understand the semantic foundation of these algorithms so that we can generalize them and improve them. Because so far, we've only looked at how these algorithms apply to a very simple first-order functional language. And we, for example, also want to apply them to a higher-order language, or a language with data types, or a language with recursion. And that's what we'll do next. I see that Benjamin Kaminsky is asking something in the chat. He's asking, was your dual number related to dual numbers of the form a plus b times epsilon, where epsilon squared equals 0? Yes, in some ways, it is related to that sort of dual numbers. In some ways, you just want to think of them as the first pair of a dual number in forward AD. You should think of as a function value, in the second value in the pair you should think about as a derivative value. So I think the most useful way of thinking about it for me is to think about them as the coefficients of a Taylor series. And we're looking at the way that functions transform coefficients of Taylor series. So it turns out that in some work that I did with Sam Staten and Mathieu Huot, we also generalized this method to a method that calculates higher order derivatives, where you don't work with dual numbers, but numbers that have multiple components for higher order Taylor series. So the first component is like the function value component, the 0th term in a Taylor series, and the second component is the first term. And that's very similar to these dual numbers in the classical sense. Okay, so let's look at the semantic foundation so we can generalize these techniques. Okay, first we'll look at the dual numbers algorithms, because in many ways they're much simpler than the other algorithms. Okay, so dual number forward AD, what does it do? Well, semantically, what we're hoping to calculate with this algorithm is that we have a function f from Rn to Rm, and then we have a sort of semantic dual numbers derivative, semantic dual numbers forward derivative. What it does is it takes an x that's a value in Rn and a v that we think of as a tangent vector at the point x to Rn, and it sends them to f applied to x, comma, the derivative of f at x applied to the tangent vector v. Right, and if we implement these forward derivatives in this way, we see that they satisfy a chain rule that's very simple. That's precisely what we had implemented in code. Namely, the forward derivative of g composed with f is the forward derivative of g composed with the forward derivative of f. And we might notice that this is a functoriality, right? We might notice that, hey, if we take as the domain category, something that I call div card, so the objects of this category are just Rn for some n, so n-dimensional spaces. The morphisms are differentiable functions. Then this functor is a functor from, or this derivative defines a functor from diff card to the category of sets and functions. Right. And the chain rule is precisely a functoriality equation. And now it turns out that it's not just a functor, but it turns out that if you do the calculations, this is a product preserving functor. So that's very nice. And that's part of why our code was so simple, because we were implementing this functor in code, and it's a product preserving functor. So we were implementing a product preserving functor or homomorphic functor in code. That's why it looks so simple. And now we can generalize this a little bit. If we don't just want to work with Euclidean spaces as inputs, but maybe smooth manifolds or some category where we can have code products of smooth spaces. Mathematicians have a natural motion of derivative on such spaces. They call the tangent bundle, which also has a functorial action that's well known. And in that case, this tangent bundle functor is again a finite product and code product preserving functor that extends this forward derivative. So again, if we were to extend our definition of the forward dual numbers forward AD algorithm to coproducts, we'd again expect it to be very simple, because this functor again preserves coproducts. In the case we have coproducts, you can think of this functor is taking a function from x to y to a function from the tangent bundle of x. So it's a sigma type of all the tangent spaces at x to the sigma type of all the tangent spaces at y. Okay, so now what does reverse AD look like, the dual number reverse AD? Well, it's something that takes a function f from Rn to Rm, and it produces a function that takes an x that's a value in Rn, as well as a linear function from Rn to C. And we think of this copy of Rn, the second copy of Rn, as the space of cotangent vectors to Rn in the base point x, if that means something to you. And the C is just an arbitrary Euclidean space in this case. And what we're sending this x comma xk, where xk is the linear function to, is the pair of f applied to x, so the function applied to x, together with the linear function where we precompose the linear function with the transpose derivative of f at x. And remember, the transpose derivative is a linear function that goes from Rm to Rn, right? Because transposition is contravariant. That's why, these types match up. So again, this satisfies this very simple chain rule that we saw in the implementation, right? The semantic reverse dual numbers derivative of g and f is the derivative of g composed with the derivative of f. So again, we have a very simple functor from diff card to set. And you can again calculate this is a product preserving functor. And in fact, you can generalize this to the world where we have coproducts. If x and y are coproducts, then this becomes something that goes from a sort of bundle of functions on the cotangent space to another such bundle. And then we get a coproduct preserving functor. So again, we expect this algorithm to be very simple because what we're trying to do in the algorithm is to implement this semantic derivative in a piece of code. So we would expect, because the semantic derivatives are homomorphic functors, we would expect the syntactic derivatives to also fully respect all the categorical structure that's present, and to also be this sort of homomorphic functor, and therefore a very simple algorithm. Okay, on to ordinary forward AD and reverse AD. And sadly, things aren't quite as simple here. And that's because the types are just a bit more complicated. But fundamentally, what's happening isn't so different. Okay, so what does forward AD do? It takes a function f from Rn to Rm, and it produces a derivative that is a function that first takes the x, so the value of Rn, then produces the pair of an f applied to x and the derivative, which is a function that takes v to d of x. Dfx applied to v. So the derivative of f at x applied to the tangent vector v. Right. So what's different from that compared to dual numbers AD is dual numbers AD takes the x and the v at the same time, and it lets the f of x potentially depend on the v. And this version of forward AD is a bit more precise in its typing, and it says no, the function value is not going to depend on the tangent vector. So we only take the tangent vector in as an argument after we've produced the output. And this again satisfies a chain rule, this derivative, except now the chain rule looks a bit more complicated. Right? You can write this chain rule as follows. So it says that T of G composed with F at X is T1 of G applied to T1 of F of X. So I write here T1 for the first component of T and T2 for the second component of T. So T1 of F is just F. T1 of G is just G. So this says G of F of X. And T2 of G is the derivative of G. And okay, so this says the second component is the derivative of G evaluated at F of X composed with the derivative of F at X, right? So this is the regular chain rule. Now, why did I write it in such a funny way? Well, it's because I want to see it again as a functor. But now the question is, what should the codomain be of this functor? So the domain, again, is this simple category where the objects are n-dimensional spaces and the morphisms are differentiable functions. But the codomain of this functor is something a bit funny. It's some sort of category that is doubled up, right? It has everything has a first component and a second component. The objects come in pairs, namely the object of a space of primal values, so function values in the space of tangent vectors, right? And the morphisms are also doubled up, namely the propagator, the forward propagator for the primal values, and the forward propagator for the tangent vectors, right? So, and we'll look at that next, what these categories look like. And they're, yeah, just sigma types of categories, or so-called Grothendieck deconstructions. And it turns out that as long as you take this codomain to be, yeah, the sigma type of commutative monoids indexed by sets, then this forward derivative becomes a functor again. And in fact, it is a product preserving functor if you calculate what the products look like in these sigma types of categories. And the intuition here is the first component of a derivative of this forward derivative is an ordinary function in the category of sets, right? And the primal values form a set. The functions, the first component of the derivative form a normal function between these sets. The second component, so the tangent vectors, form a commutative monoid because you can add them to each other. We saw that addition is important for automatic differentiation. And the derivative is a linear function. So that's why it's sort of set doubled up with commutative monoids. And now, again, we can come up with a version that also works for coproducts, and then it becomes a coproduct preserving functor. The types just become a bit more complicated. We get some dependent types lying around. Right. And we can do something very similar for reverse AD. And we see that the only thing that's changed is our derivative has become a transpose derivative. Our order of composition has changed here in the derivatives in the chain rule. And because of that, we just need to add an opposite category to commutative monoids. But again, it becomes a product preserving functor. So again, the idea will be forward and reverse mode derivatives in the semantics. So the thing that we're trying to implement with our AD algorithm are homomorphic functors in some sense, as long as we choose the right categories. And I think that's maybe why people hadn't immediately noticed this, because the codomain category of this functor is this weird sigma type of categories. So that means that the products and the coproducts, and especially the exponentials, look a bit funny. So you might not notice that the algorithm is very simple, but it really is if you notice what the products or what the categorical structure is like of these sigma categories. So that's what we'll look at next. So we'll look at, yeah, what are these sigma categories precisely? Okay, so the starting point, if we want to build one of these sigma types of categories, is a so-called indexed category. So that is, we assume that we have some functor L, some contravariant functor L from a category C to the category of categories. So that means that for each object C of C, we have a category L of C. And for each morphism in C, we have a substitution functor that goes in the other direction from L of C prime to L of C. Right, and in case we have a real index category here, we're in the situation where we have potential type dependency. So that'll come up in derivative land whenever we consider co-products, because then we get these complicated dependent types. But as long as we don't care about differentiating at co-product types, then we can focus on the simpler case where we don't have any type dependency, where our spaces of tangent vectors or cotangent vectors don't depend on the primal base point that we choose. So, and in that case, we're working with certain degenerate index categories that you call locally indexed categories. So this is the case where the objects of all the fiber categories are the same, and the substitution functors between the fiber categories are identity on objects, right? So that means the types in the fibers do not depend on programs in the base category. Or I guess in derivative land, the dimension of the space of tangent vectors or cotangent vectors does not depend on the value that we choose at which we evaluate the derivative. Okay, so the intuition here is the objects of C are certain Cartesian types, so something that resembles sets. And the morphisms from C to C prime in C are just regular functions that take input of type C and produce output of type C prime. The objects in L of C are linear types that potentially depend on C. So there, in our case, they're going to be commutative monoids that depend on the set C. So families of commutative monoids indexed by the set C, or in the case that we don't consider coproducts, they're just going to be a fixed commutative monoid. They're going to be a constant family. The morphisms in L from L to L prime in L of C are going to be functions that take an input C that is just a regular functional input, and then a second input in which it needs to be a homomorphism. Okay, so that's the intuition here. And now, given such an index category, we can form one of these sigma types of categories. And what they look like is the objects in the sigma type of C and L are going to be pairs of a C that's an object in C and an L that's an object in L of C. Morphisms from C, L to C prime, L prime are going to be morphisms C from C to C prime, paired with a morphism L that goes from L to not L prime, but an L prime that we've sort of substituted such that it's in the same fiber category. The identities are going to be pairs of identities, and the composition is going to be a bit funny. In the first component, we take regular composition. In the second component, we take regular composition, but aided with this weird substitution of a C. And what you're seeing here is that the composition formula in this sigma type category, you might recognize it because it's precisely the formula that we got here in the chain rule, right? We have regular composition in the first component and this sort of funny composition in the second component. So this funny composition in the sigma type of categories is going to make sure that the derivative is a functor. And here's a little illustration of how that composition works. Okay, so this is one thing we can do. We can build a sigma type of the category L, but we can also do something else. We can first build another index category out of L by dualizing all the fiber categories, and then take the sigma type of that. And that's going to be the codomain of the reverse derivative, right? That is one of these things where we've upped the category of commutative monoids. Okay, so now you know the ingredients to understand the basic principles behind chat. And now we'll start to zoom in more on what precisely the categorical structure of programming languages as categories looks like, and what the products and co-products and exponentials look like in these sigma types of categories, to then derive what the automatic differentiation algorithm should look like. Okay, so the basic principle behind chat, so what I've been calling combinatory homomorphic automatic differentiation, are we're going to implement these derivative functors that everyone uses in mathematics, except no one calls them functors, in code. Now we're observing that these derivative functors in mathematics are already homomorphic functors, even though people don't tend to emphasize that. So they preserve products and co-products and such. Now, this is good if we want to differentiate on a first order language, but we might also want to differentiate programs that don't have a counterpart in traditional mathematics, right? as higher order functions or recursive functions, we don't normally learn what the derivatives of these functions are. So the way we're going to do it is we're going to say, okay, let's just again assume that derivatives act homomorphically on all of these new features that we add to our programming language. Just extend it in that way. But then it's not so obvious why the algorithm is correct anymore, because there is no semantic counterpart. There's no normal notion of derivative of a higher order function that everyone agrees on. But then we can see that we can get a good notion of correctness, namely that the derivatives only produce correct results at first order by using a logical relations argument. And that works very, very well because all our definitions are homomorphic functors. Okay, so that's the basic story. And now to execute this recipe, we first need to notice that all programming constructs that we use in functional languages basically have an equivalent in category theory. Right, so if we have certain ground types, like types of real numbers or integers, that's like having certain designated objects in our category that we call integers or floating point numbers. Our primitive operations, so these are operations that cannot be further decomposed into more basic building blocks, are going to be just designated morphisms that we need to have in our category. Having tuple types or record types corresponds to having finite products. Sum and variant types correspond to having finite coproducts that are distributive. Okay, so this is the nice story so far. This is the story where we can precisely follow the semantics in our implementation of AD, because we have a semantics of derivatives and tuple types and record types and sum types. But now we want to go further, right? So we say, okay, we also want to add function types and inductive and co-inductive types to our language, or recursion, iteration. And we just look at what the categorical axiomatization is of that structure. We add that to our programming language, and we demand that AD becomes a homomorphism of that structure. So I'm just calling that structure S now, and it's going to be that S is going to be parametric in whatever you want to have in your programming language. Okay, so then the first thing to do will be to consider the source language as a category, and it will be a very simple, freely generated category. And we call it SYN. So we will see that the source language, so a standard programming language like a simply typed lambda calculus can be seen as a freely generated category with structure S, where S is the set of features we want to have in our language. Then we choose a target language for automatic differentiation, which may not be the same as the source language. In some cases it is, in other cases it's not. Typically it's going to have some notion of linear types. And we see that we can build another S category out of this target language. So this is going to be the language that the programs that automatic differentiation produces land in. The source language is the language where the programs that automatic differentiation consumes come from. And then we see that automatic differentiation becomes the unique canonical S functor, so the canonical homomorphic functor from the source language to the target language, which we know exists by the universal property of the source language. Then we can take a few more steps. We can see, hey, we can again construct the semantics in terms of sets for the source language as another one of these homomorphic functors. We can construct a semantics that I call tsem for the target language. So again, it's going to be a structure preserving functor. And then the correctness proof will be another structure preserving functor by building a certain category of logical relations over the product of the semantics of the source language and the target language. And then the correctness proof will basically be to notice that a certain diagram commutes, and it needs to commute because both sides of the diagram are going to be a homomorphic functor that agree on their action of the generators of the source category, namely the primitive types of real numbers and the primitive operations. And that's something to check manually. But once you check that the derivatives are correct on the primitive operations, so for all the basic building blocks, then because everything, the semantics and the definition of AD are homomorphic and compositional in this sense, it automatically follows that the derivative of an arbitrary program is also correct. Okay, so this is the very high level picture. The only thing that I haven't said here now is, what is this target language? And what is this target language semantics? And that's precisely how the different AD algorithms will differ from each other. So for dual numbers style AD, it's very simple. We can choose the target language to basically be the same as the source language. In this case, I write CSIN for it, so that I mean it's a target language with Cartesian types. So the C means Cartesian types. The semantics of the target language is again going to be just in terms of sets and functions. For non-dual numbers AD, the story is a little bit more complicated. What we need to work with is a language that has both Cartesian types and linear types. And maybe the linear types should be allowed to depend on the Cartesian types if we want to be able to differentiate coproducts, but it's not necessary if we don't add coproducts to our language. And it turns out that in practice, we never need a type dependency. I'll talk about that tomorrow. Okay, so then the target language becomes the sigma type of categories of the category of linear types indexed by the category of Cartesian types. And for reverse AD, the only difference is that we add a little up to the world of linear types. That is because the monoid homomorphisms go in the other direction because we're taking transpose derivatives. Okay, so let's dive into what these syntactic categories are. And I think that's where we'll end today. Oh, yeah. One more thing I wanted to say here is the semantics for the target language is going to be the intuition that I've been giving you the whole time, and that is that the Cartesian types represent sets, the functions, the programs between Cartesian types represent functions, the linear types represent commutative monoids, or maybe families of commutative monoids, and the programs with linear types, the homomorphisms represent monoid homomorphisms. Okay. So the last bit of this talk for today is going to be programming languages as free categories. And let's first look at the source language. Hopefully this is a story that you've sort of seen before. But it's the idea of how you can see functional programming language as a very simple category, namely a freely generated category. So the idea is that the objects of the source language are types. Well, I say Cartesian types because the only types we have in the source language are Cartesian types. But later we'll see that in the target language, we also have certain linear types. So what that means is we have certain basic types that aren't decomposable. So there are things like arrays of real numbers or integers. And then we have composite types that we build using products, coproducts, exponentials, the standard operations you have on types in the lambda calculus, right? These are going to be the categorical products, the categorical coproducts, and the categorical exponential. Now, the morphisms in your category, the morphisms from tau to sigma, are going to be programs that take an input of type tau and produce an output of type sigma, but considered up to beta eta equivalence. Okay, and we'll see that these programs, well, they're generated from a certain basic building blocks, namely the primitive operations that we add to our language that are operations that we can perform on our primitive types. So things like cosine and exponential, multiplication of real numbers, the basic building blocks that we add to our language that we then are going to specify how you differentiate them. And then we build composite programs in all the usual ways, right? So we have variables, we have let bindings, we can apply operations to arguments, we have lambdas, all the usual functional programs. The identities are just what you'd expect. They're just variable references. Composition is done with let bindings. And now the important part here is that this category has a universal property, right? And this is precisely the sense in which this is a freely generated Cartesian closed by Cartesian closed category on the objects that we use as generators and the morphisms we use as generators. Namely, given any other bi-Cartesian closed category C, as long as we make a choice of an object f of t, which is going to be an object of C for all the generating objects of our syntax, or for all the basic types of the syntax, and as long as we choose a well-typed morphism in C for all the primitive operations in our language, this assignment extends to a unique homomorphic functor from the syntax to C. Okay, and we're going to choose C to, for example, be the target language, the syntactic category of the target language. And then what we get is we get that there's a canonical definition of automatic differentiation that's homomorphic the moment we specify what the derivative is of each primitive operation. Okay, so that's the source language. Let's now look at the target language. The target language is a language that has two kinds of types in it, generally. And that turns out to really be important for AD. We have some Cartesian types, we have some linear types. It turns out it doesn't really matter for the implementation. You can implement all of this in a standard functional language like Haskell. You can implement the linear types as basic abstract data types. That doesn't matter, but it just gives you a little bit of extra type safety. And conceptually, it can be nice to consider them as linear types and to distinguish them from the Cartesian types. Okay, so the Cartesian types we think of as denoting sets and functions, or the programs between these types we think of functions. The linear ones we typically think of as certain kinds of algebras, and the programs with linear type we think of homomorphisms between these algebras. So in the case of automatic differentiation, the relevant notion of algebra is a commutative monoid, as we saw in the example. Okay, so generally, whenever you see linear types, there's some notion of impure computation going on, and there's some algebraic theory of operations and equations that these operations satisfy. In the case of AD, the relevant algebraic theory is the theory of commutative monoids. So we can build composite linear types from basic linear types in the same way that we could for Cartesian types. So we might have certain primitive built-in linear types, for example, the type of n-dimensional real arrays, which we think of as the type of tangent vectors or cotangent vectors to Rn. We consider that as a built-in type, and then we have composite types. For example, we can take the product of two algebras, we can take the power of an algebra with a set, we can take the co-power of an algebra with a set, we can build a free algebra out of a set. And then if we have two algebras, we can form a set of homomorphisms from one algebra to the other. And we can take the underlying set of the algebra. And these two things are going to be Cartesian types again. So this is a sort of type system that's similar to the enriched effect calculus or Levy's callback push value that you may have seen, or just a form of linear logic. Okay, so we have programs here in this sort of language. We have programs that have Cartesian inputs, Cartesian outputs. So we call those functions. We think of them as functions. Then we have homomorphisms. So they're things that have some Cartesian inputs in gamma and have a single designated linear input and produce a linear output. So the way we think of those are as families of homomorphisms from the monoid or the algebra that tau represents to the algebra that sigma represents. And then we have computations, which you can see as a sort of special case of functions or of homomorphisms that we think of as the elements of the algebra. So normally, okay, right. So this sort of language you can think of as the internal language of certain locally indexed categories with products and powers and co-powers, etc. And then if you consider linear dependent types, it becomes internal language of a certain kind of indexed category. Right, where the Cartesian world is the world of the base category, and the linear world is the world of the fiber categories. Okay, so now generally we can apply the operations of an algebraic theory in such a linear language only to computations. So that means that we can apply the operations to elements of the algebra. Which justifies the name homomorphism. And in case we have a commutative algebraic theory, which is the case in our case, because we're looking at commutative monoids, we can in fact apply them to arbitrary homomorphisms. So we can add two homomorphisms and we have a zero homomorphism in the world of commutative monoids. And I'd like to note here that it's relevant that we're working with commutative monoids. That's relevant in practice because we tend to parallelize these automatic differentiation computations, and the commutativity means that it's quite easy to parallelize this sort of computation because the order doesn't matter. So as an exercise, maybe you can look at what the power and co-power and such look like in commutative monoids, if you haven't seen that before. Okay, so now we have a category. I'm going to end here. We have the target language as a category. So we have a base category of Cartesian types. We call it CSIN, Cartesian types and functions. This category has finite products, co-products and such. And then we have a locally indexed category of linear types that I call L-syn over C-syn that has linear types as objects. And it is a commutative monoid enriched category because the homomorphisms form a commutative monoid. And this has powers, co-powers, etc. Okay, so now we've constructed the linear, the source language as a category, the target language as a category. We'll see next time that all these categories, well, we already saw that the source language has all the relevant categorical structure. Next time we'll see that the target language does as well. And then therefore we get, I guess, a unique homomorphic functor from one to the other. That is going to be the definition of automatic differentiation. So the crux next time will very much lie in the categorical structure of these sigma type categories. And by looking at what that structure is, we can precisely calculate what the definition should be for automatic differentiation. So I'd like to end here.
Thank you.
I don't know if there's any time for questions. Sorry for talking for so long.
So we're running a little bit behind schedule. So if someone has a burning question from the room or online, if not, Matthijs is going to give another 45 minutes tomorrow. So you could also ask offline if you want.
Yeah, feel free to email me or yeah, I'm always happy to discuss.
Hello. So this sigma type of categories, is it a dependent sum in some formal sense about cat?
Yeah, I would guess so. I haven't thought about it enough, but yeah, my intuition is sort of, yeah, you probably have a model of dependent type theory where the interpretation of types are categories, the interpretation of dependent types are index categories, and then the sigma type in that model presumably would be this Groton deconstruction, or the thing that I call sigma type of categories. Obviously, this works for groupoids. I haven't looked at whether it works for categories, whether you really get a model of dependent type theory. But the intuition is clear, right? This is a sort of generalization of the sigma type of sets or groupoids to a sigma type of categories. Yeah, people normally call it the Groton deconstruction, but I don't find that name very compelling because Groton came up with a lot of constructions.
But did you know if cat is locally Cartesian closed?
I haven't really thought about it. Yeah, I haven't normally seen people consider these pi types of categories, if that's what you're asking, but people consider
no, just to, because I do know Groton deconstructions and like this sigma type that you do, but I never thought to connect them as well, and it's a very beautiful story.
Yeah, I don't know. It's a good question. We'd have to look at it. It's yeah, but it was more of an intuition that I tried to convey, but it could be that it could be made formal as a model of dependent type theory.
We have one more burning question.
Hi, thank you for the talk. If you apply your two functors forward or reverse to a pure simply type lambda term, what do you get? Because the target category is no more the lambda calculus. So what you get?
Yeah, so you get something that's I see, by the way, that Fernando answered a previous question in the chat that cat isn't locally Cartesian closed. Thanks, Fernando. Yeah, if you apply this to a simply typed lambda calculus, you generate programs that aren't just like standard simply typed lambda calculus programs, but they have some linear types in them. In the case of forward AD, they have some powers in them. In the case of reverse AD, they have some co-powers in them. We'll see that next time. It has to do with the precise structure of these sigma types of categories. But yeah, it is code that you can implement just in a standard functional language quite easily, because all the linear types that you need, you can implement as an abstract data type. Yeah, I will link to an implementation if you're interested.
Okay.
But it's
okay.
Yeah, so by contrast with dual numbers AD, what you generate here really goes beyond the simply typed lambda calculus, right? Like forward mode dual numbers AD, The source language and the target language are just a simply typed lambda calculus. Reverse mode dual numbers AD, you already see that to get the complexity to be right, you need some linear types, right? And you need a non-standard operational semantics. In the case of this sort of forward and reverse AD, you need some linear types as well, but you don't need a non-standard operational semantics. You can just, yeah, you can quite easily implement it in Haskell without using an interpreter.
Okay, so let's thank Matthijs again, and he will continue tomorrow.